So in 2.9, we've got the rank theorem, and we also introduced the concept of coordinates. So remember, with coordinates, we have vectors in a subspace. We want to write linear combinations of those vectors in the subspace relative to some basis. So the vector x, if H is a subspace, say, of R3, then vector x is in R3. But if H is a two-dimensional subspace of R3, then the coordinates of x relative to B will be in R2. So x and its coordinates might be in different spaces of subspaces of Rn, or different Rn's. So let's look at an example. Let's look at an example. I'm going to pull 2.9, number 6. We have here x is in a subspace H, and B is B1, B2 is a basis for H. So B equals B1, B2 is a basis for subspace H. And in problem 6, B1 is the vector -3, 2, -4. B2 is 7, -3, 5. And x is 5, 0, -2. Okay. So in this case, we'll want to write the coordinates of x relative to B. So we're given that x is in H. We're not sure of that. I don't really trust it yet, but we want to find the coordinates of x relative to B. And in this case, we're assuming x is in H. Well, we're given that x is in H. What this means, this question says, write B as a linear combination of B1 and B2. So write x as a linear combination of B1 and B2. So find the coordinates of x relative to a basis means write the vector as a linear combination of the vectors in the basis. All right. So first things first, notice that H is a subspace of R3, but the coordinates of x relative, it's a two-dimensional subspace of R3. So the coordinates of x relative to B are going to be in R2. So H is a two-dimensional subspace of R3. So H is two-dimensional subspace of R3. So that means the coordinates of x relative to B are going to be in R2. This does not mean that H is equal to R2, because the vector 5, 0, -2 is 100% absolutely not able to be in R2. It's got 3 entries. It can't be in R2. It just can't be there. So we want to write x as a linear combination of B1 and B2. That is, we want to solve C1 B1 plus C2 B2 equals x. We're trying to solve this equation. And the way we're going to solve the equation is the same way we solve every equation, with an augmented matrix and the reduced echelon form. So I'm going to make an augmented matrix with B1 and B2 and x. I'm going to find the reduced row echelon form. I know what the first 2 columns are going to look like, because if they don't look like this, I ain't got a basis. I just need what that 3rd column is going to be, and I can't just see it. So, oops, this is way too much, but I'll do. So I need -3, 7, 5. 2, -3, 0, close, open, -4, 5, -2, close the row, close the matrix, close the command, and get rid of all the rest. So -3, 7, 5, 2, -3, 0, -4, 5, -2. -3, 7, 5, 2, -3, 0, 4, 5, 2. Double check that I copied everything, and it's 1, 0, 0, 0, 1, 0, 3, 2, 0. 3, 2, 0. So we're solving, here's C1 and C2. We're trying to solve a vector equation. And so I get C1 is equal to 3 and C2 is equal to 2. What this means is that 3 times B1 plus 2 times B2 is equal to X. There's X as a linear combination of the vectors B1 and B2. That means that the coordinates of X relative to the basis B are 3, 2. So notice that the coordinates of X relative to B are in R2, but the vector X is in R3. This is because X is an element of a two-dimensional subspace of R3. That two-dimensional subspace of R3 is isomorphic to R2, but it is not equal to R2. As mathematicians, you're going to have to find out, you have to clarify what you mean by equal. And find things that are, and what you mean by equivalent in different situations. Any questions? If I told you, for example, if I added on to this in 2.9 part problem 6, alternate version, if I told you that the coordinates of y relative to b were -5, 1, oops, scroll up. If I gave you the coordinates of y relative to b, I'm giving you the linear combination of the columns of b that gives you y. So you could say that y equals -5 times b1 plus 1 times b2. That's what I mean when I say the coordinates of y relative to b are -5, 1. That means y is -5 times b1 plus 1 times b2. So that would be -5 times the vector -3, 2, -4 plus 1 times the vector 7, -3, 5. Notice that we're going to get a vector in R3 because y is an element of H, which is a subspace of R3. So y is in R3, even though the coordinates of y relative to b are in R2. So what this is, 15 and 7 is 22. -10 minus 3 is -13. 20 and 5 is 25. So there's the vector y. Here are the coordinates of y relative to the basis b. Any questions? Another important thing to note, we've taken, so H is a subspace, a two-dimensional subspace of R3. So H is a plane in R3. And that means that the span of, I'd have to build a matrix. So we're breaking H into everything that's in this plane and everything not in this plane. And so that would be a line. So there's a line left out of this plane, and that's the third piece that's missing. Any questions? Also note that H is the column space of the matrix -3, 2, -4, 7, -3, 5. So this is one of the reasons that column space and null space are important. If we're looking at the span of a set of vectors, we can say that it's the column space of a matrix. Right. Any questions from other questions about 2.9? How are we doing with coordinates? Is it easy? How's everybody? Any other questions that I want to go over in 2.9? A lot of these questions are thinking about the size of the matrix and where the pivots are. So once you get to problems 19 to 24, justify each answer or construction. If the subspace of all solutions Ax equals 0 has a basis consisting of 3 vectors and A is 5 by 7, what is the rank of A? So there are 7 columns. 3 of them are non-pivot columns. And that means there are 2 of them that are pivot columns. So it's just about looking at where the pivots are, using the rank theorem, that every column of a matrix is either a pivot column or a non-pivot column. Pivot columns contribute to the dimension of the column space. Non-pivot columns contribute to the dimension of the null space. Any questions? Cool. If there are no more questions for 2.9, let's pause the video on 2.9 discussion and think about where we're headed next.